started with it. It's not as easy as the one that we just did. So looking at this unit, like I do want you to see, like it is another kind of fairly short one. It's basically going to be 1 week before spring break, and then we'll finish it the week after spring break. I do have it in my plans where I could push back the tests until like the following Wednesday. That would cut into like our AP review time. It kind of just depends on how those 3 virtual days where we have shortened periods kind of go. But it's really just, I don't want to say just, but it's 3 main topics. So it's like the idea of a differential equation and analyzing it, something called solving a separable differential equation, and then a certain type of differential equation word problem. This week, obviously kind of weird. Many of the juniors will be taking the ACT, so everyone else just have kind of a day at home. And we're going to try to get done 2 topics this week. I did realize after first period there are going to be some things that I need to go back and like reteach, especially for some people who came out of GABs and probably some people who had me first semester and just forgot, which is fine. So I'll probably have to adjust a few of those days this week and just reteach mainly implicit differentiation. But other than that, it is kind of a straightforward unit. It is a nice one to end the year with, because by its name, differential equations, you can kind of assume there's going to be quite a bit about derivatives in there. But it does also attach to like what we've been doing with the intervals. I like teaching this unit last because it really allows me to start doing AP exam review stuff within the unit. So like derivative rules going to show up, integration rules going to show up, tangent lines, relative extrema, concavity, all those are going to show up. Implicit differentiation, it's going to show up. So it has a lot of first semester topics kind of mixed together with second semester topics. What we're going to be looking at today is going to be something called slope fields, and then kind of just ways that we can analyze slope fields. I will say the first homework we have, it is kind of disjointed because there's going to be just like a lot of topics you have to review. It's not a long homework, but it does have like, on homework 1, there's like no 2 problems are going to be done exactly the same way. So there's going to be a much more of a unit where you have to like think to solve it. I know think, but like some critical thinking, kind of like reasoning, and not just like solve it and get to an answer. So it is going to be a little bit different from the previous one. And what I wanted to start off with today is just something called differential equations and slope fields. So before we get started, I did want to go ahead and define what a differential equation is. And the easiest way I can talk about it, we actually saw this definition back in Unit 5, but a differential equation is basically an equation with derivatives. Again, to make something an equation, you have to see an equal sign in the problem. And then if it has a derivative, it can be any type of derivative. So it might be like the first derivative. It might be the second derivative. We'll often write in the dy dx notation, but any type of derivative, as long as you see an equal sign in derivative, we're going to call that a differential equation. On the bottom of that page, kind of in the different colors, I just have like a bunch of differential equations. Some of those I think are recognizable, some of them not so recognizable. Like that first one in kind of the teal color, or I guess light blue, y prime is equal to 5x plus 6. That's just the first derivative of something, but that is technically a differential equation. The lime green one, that would be something that's kind of new for this unit, where we have like the derivative is in terms of y instead of in terms of x. That orange one, we have like an equation that both has a first and second derivative in it, which is kind of unique. And then like that purple one, y prime is equal to x times y, or like y prime is equal to x squared plus y squared, where we're kind of mixing together the x's and the y's. Things that we want to be able to do with the differential equation: analyze it, interpret it, which is kind of a pretty broad thing that we're going to do. And then the other thing is basically going to be something called creating a slope field, which this has been a common question more recently on the free response section of the AP exam. If it is a free response question, like you want to be glad it is, because it's one of the easier ones you can see. So what is a slope field? A slope field is basically what it sounds like. it is going to be in some ways like a field of slopes. What do I mean by that? We have a differential equation. The differential equation is 2 times x, and we have a whole bunch of points. And on that graph, you can kind of see where I have just a bunch of dots, and we're going to draw like little baby slopes, if you will, at each of those coordinates. How do we do that? Well, dy dx, again, that's just the same thing as saying y prime. For differential equations, we tend to use, again, the dy dx notation. We'll get to y a little later this week, but that is just y prime. This is calculus. What does y prime represent? The slope at a point. So if I want to find the slope at -1, 0, if dy dx is 2x, I can just plug in the x coordinate. 2 times -1 is -2. So then I'm going to go to that point on the graph and just estimate it by drawing like a little hash mark, a slope of -2. Doesn't have to be perfect, but it should be decreasing. So there's my slope of -2. And then it becomes more tedious. You just have to kind of repeat that for every single coordinate that you see. Hopefully you pick up some patterns. So like this differential equation, there is no y in it. So it's only reliant on the x coordinate. So I pretty much know that whenever x is -1, the slope is always -2. And again, I'm just kind of estimating what that would look like. It doesn't have to be perfect. When x is 0, 2 times 0 is 0. So the slope is 0. What's the slope of 0? That will be horizontal. And then just kind of keep going. When x is 1, 2 times 1 is 2. So now it's going to be an increasing line. And then when x is 2, 2 times 2 is going to give you 4. So I just want to draw something that appears steeper. If this was an AP question, it's actually graded pretty leniently. Like I know I had one this year that had a slope field, and I just had to look for slopes that were horizontal should be horizontal, slopes that were positive should be increasing, and slopes that were negative should be decreasing. Now, to be more exact, all the ones that have the same slope should be parallel, but when you're doing it by hand, that's not going to be really necessary. Why do a slope field? So there's 2 ways a slope field can be given to you. It's either going to be one that you create yourself, or it could be one that's computer generated that has a whole lot more kind of like the little tick marks on it. Why is it useful? It can help you figure out what the original function could look like without having to like integrate or do anything like that. I chose this one because it's a fairly easy one. I know we can all easily find the antiderivative of that one. But let's talk about it in terms of the slope field. I'm going to go to the next slide because I was also lazy and used a computer to draw that slope field, only because I wanted to have something a little bit more exact to kind of talk about. But if you look at the words underneath that one, it says on the axes provided, so either on the one you drew or the one that I have, I want you to sketch the graph of that particular solution that goes through the initial condition f of 0 is equal to 1. What does that mean? We know when we see particular solution in this class, that's like the original function. And we have the initial condition f of 0 is equal to 1. So I know that f of 0, 1 is a coordinate on this graph. So I know that point is there. And then think of this as like the calculus version of like connect the dots. But now we have a little like slope field, and they're just going to kind of push you in the direction you should go. If I'm going through that point, what shaped graph is going to be drawn if you kind of just like look at that slope field? It looks like a parabola. So again, think of these, some people, I like think of them as like little wind currents or like currents in the water. Like it's going to be horizontal, pushes you up, horizontal pushes you up. But it does form a quadratic. And we could use the slope field to help us make that determination. Now this one is one that we actually know how to do. We actually did this, we could have easily done back in Unit 5. We know how to find the antiderivative of this one, which is what we call the general solution. If we say, so I'm just kind of rewriting it, if dy dx is equal to 2x, what would I need to do to figure out what the original function is going to be? Take the integral. What's going to be the integral of 2x? X squared, what do you want to remember? Plus the C. And that C is important because that's basically what the slope field is saying. You can kind of imagine if you didn't have the initial condition, that slope field is just like all the possibilities of plus C. It's all like an x squared plus something, depending on what that starting position is. You can kind of imagine how that slope field is related to the general solution. How do you find the particular solution? Well, this is the general. We know that when y is 1, x is 0. So C is equal to 1. So I know that for the particular solution is y is equal to x squared plus 1. Now I chose this one that we know certain things about. That is the particular solution. Well, what is the equation of that graph we drew up here? X squared plus 1. So you can kind of see how the slope field does kind of check out with what the algebra and the calculus means. Now, normally you're not going to be making a slope field for something that simple, or one that you could easily find the antiderivative of. A slope field is going to be more important when you have like some stranger looking derivatives. Maybe it's a derivative that's in terms of y instead of x. Or maybe it's a derivative that has both x's and y's playing a role in what that slope field looks like. So go ahead for me and try this next one for me. See if you can draw the slope field for that differential equation. And again, you don't want to overcomplicate it. A differential equation is just the derivative. The derivative represents the slope. Plug in those coordinates and draw your little baby slopes, and then that would represent the slope field. Again, how are they used? We'll talk about how we can make predictions using that slope field. As you're working on it, some people are like, Mr. Brown, this takes forever to do, and you're like, okay, yes, it's tedious. I will say on the AP exam, the most number of like points I've seen you have to plot is 9 maximum. Sometimes it's even less than that. So this one's probably even like twice as long than like the average AP problem they ask you to make a slope field with. The other types of questions, they'll have one already generated for you, and you can kind of interpret it that way. Notice this one's a little bit different too. Instead of being 2 times x, it's 2 times y. So basically you're plugging only the y coordinate in to find all of these slopes. So like 2 times the 0 is 0 whenever y is 0. We know the slope is 0. And you can pick up on those patterns to help you do it faster. Like whenever y is 1, the slope is going to be 2. And that's kind of one way to speed it up a little bit. And again, they don't have to be perfect, but should be at least kind of close enough. So there's my slope field. Again, things that are important, slopes that are 0 should definitely be horizontal. All the other ones should be positive. Of course, the ones at 4 should be a little bit more steeper than the ones at 2. How these are important is they can help us make some conclusions about this differential equation. But Mitch, you had your hand up.
Yeah, can I go to the restroom?
Yeah. So this dy dx is equal to 2y. I do want to be clear kind of about this derivative. At this point, so this will not be true later in this unit, but at this point, that is not, it is easy, but right now for us, it's not that easy to find the integral of, because it is in terms of y, not x. So we can't take the integral of this like we normally would. But we can use the slope field to help us draw conclusions about what the original function potentially looked like. What type of function would you guess has a derivative that's equal to 2 times y? Just looking at that slope field. It looks exponential. So like things that we can kind of start talking about is, hey, this looks exponential. So I don't know what y is. I don't know what the original function is, but it's probably going to be some sort of exponential. There's different things we can do. So eventually we would actually be able to solve it and find the exponential equation. We're not there yet. But let's go ahead and I'm going to use the computer generated one just so it's a little bit more exact. Same thing, let's go ahead and draw the particular solution that goes through the initial condition f of 0 is equal to 1. So again, you know that coordinate is on the slope field, f of 0 is equal to 1. And then just let the slope field be your guide. So again, kind of like fancy connect the dots. Moving towards the left, it goes down. I see the slope fields flatten out. And up here is just going to keep increasing. So we can see it does have like an exponential look to it. Sometimes I have students ask for like, well, Mr. Brown, why couldn't you just keep going straight down? And they might try to draw something like this. And they're like, that's how the slope field pointed to me. But you're crossing something that has like horizontal slopes. So you're not ever going to go like against the grain. Like you're always going to go with the slopes. They're going to guide you gently in the correct way. So that's kind of looking at slope fields. Some things that we're sometimes asked to do. So again, we can't solve this one. We can't find the integral of it. So how that question might be worded instead is it says verify that y equals e to the 2x is a solution to the differential equation. A lot of students find these questions weird, and I understand why. But whenever you see the words verify, sometimes they'll use the word show. The question is giving you basically the starting and the ending point. You have all the information you need. You just need to show how two different things are related. So like what's going to be graded as your steps. So it's telling you, we want to show that this y is a solution to the differential equation. Which one? I'm just going to rewrite it. That was 2 times y. So what that question is basically asking, we want to show that y equals e to the 2x has a derivative of 2 times y. Take a guess. What do you think you might need to do to kind of show that y has a derivative of 2 times y? You guys make a guess. Let's take the derivative. So we don't know how to integrate this, so we can't really do it that way. But let's just go ahead and take the derivative. So this would be y prime or dy dx. I could use either notation. What's the derivative of e to the 2x? 2's, all right? So we have anything, e to the u is just e to the u. And then don't forget the chain rule, so times 2. We know y prime and dy dx, those are exactly the same thing. And what this question is asking us is we want to verify, so we know it's true. We're verifying that what I have in blue is exactly the same thing that I have in red. When it says show, like again, we know what the answer is. They are equal. We just need to kind of clearly show how we know they're the same. Well, how can I show they're the same? I know this one is 2 times y. This one over here is 2 times e to the 2x. Well, what is e to the 2x equal to? Don't overthink it. What is e to the 2x equal to?
Y.
E to the 2x is equal to y. So just do some substitution. So y prime is equal to y times 2, which is clearly the same thing as 2 times y. Once your two sides are the same, you have verified. You don't need to write words. You don't need to like explain it. You just have to show it. So either students try to make that more complicated than it is. But again, just think whenever you see the instruction, the two sides are the same. You just have to somehow start plugging in things and doing stuff until they are the same. Last slope field, and we'll do another one of these verifying ones as well. Probably the most tedious one to make. Here's a differential equation that is in terms of x and y. So you would have to plug in both the x and the y. The pattern is not going to be as nice to follow. But again, that is still a derivative. What is the derivative? The derivative is basically 2 times the x coordinate minus the y coordinate. You can plug those in. And then again, just kind of estimate by drawing in those little baby slopes. Things that are important, positive slopes should be increasing, negative slopes should be decreasing. Slopes of 0 should be horizontal. Don't have any for these, but if you have like a number over 0, then that should forfeit an undefined slope or a vertical line. But go ahead and do this one. Again, probably the more tedious of them. And then we'll talk about how we can analyze it, and then we'll do another verifying type problem. again, this one definitely a little bit more tedious to do. Again, don't stress about trying to make your slopes perfect. You are doing this by hand, so it's not going to be a perfect slope field. What is important, I kind of color coded it. Ones that are decreasing should be clearly decreasing. Ones that are 0 should be clearly horizontal. And then ones that are positive should be clearly increasing. Looking at that slope field, if you had to make a guess of what type of function that slope field looks like, any guesses of what it could possibly be related to?
Could it be like an x cube?
You might say it's cube. I would actually say it probably looks more like just a U-shaped graph, because of the way you see ones going down and then up. It's actually not like any family of functions, so it's going to look most like a quadratic, but this is kind of why slope field is important. It's not going to be actually perfectly symmetrical when we do it. But again, it's kind of nice to think about, hey, we can at least look at the slope field and say, hey, maybe more on the left-hand side of the graph, it appears to always be decreasing. More on the right-hand side of the graph, it tends to be increasing. There's a horizontal tangent probably in the middle. But again, we're just talking in general terms, how can we make some sense of that slope field? So again, similar questions that we had in that previous one. There's the computer-generated one that's a little bit more exact. On the axes provided, see if you can sketch a particular solution that goes through f of 0 is equal to 1. So again, f of 0 is equal to 1. And again, I could have chosen any initial condition. I just happened to choose that one. And then let the slope fields kind of be your guide. So you're not going to cross over any of them harshly or anything. So I see this side, I'm just going to kind of follow it going up. This side, I do say some students try to make it to just always kind of go down. But if you always go down, you kind of hit in this area that's kind of like a dead end and not so smooth. Slope fields are always going to create kind of smooth curves rather than jagged ones. So it makes more sense to me to do something like that. Again, if you are just throwing it in, you are just doing some sort of prediction. What is important is eventually two things will happen. Either we will know how to find the antiderivative of it. I will say this one is one that we never learn how to find the antiderivative of it. It's just one that we can kind of estimate. I did go ahead just because I know where it came from. That is a possible original function that has that as its derivative. So it is definitely not one of our fundamental functions. It's this exponential with a linear term in it. Again, when we see verify, it's giving us all the information we need to know. We know what the function is. We know what the derivative is. We just have to show that they are directly related to each other. I'm going to rewrite the derivative. It was dy dx is equal to 2x minus y. And we want to show that this y and that dy dx are directly related to each other. So again, we just need to fill in the steps in the middle. What might be something you want to try first? Let's take the derivative. So I have y prime, could also use dy dx. 3 is a coefficient, e to the negative x. What rule do I also need to remember? Chain rule. So times -1. The derivative of 2x is just 2, and the derivative of -2, of course, goes to 0. dy dx and y prime, remember that's just the same thing in different notations. I need to somehow show that what's in red is exactly the same thing as what's in purple. Don't make it more complicated than it needs to be. Similar to that other one, you want to find something to plug in and substitute. And if you try to make it more complicated than it needs to be, that's when students try to make mistakes. What's going to be the easiest thing to substitute in? Typically, if you see a y on either side, that's going to be the easier one to plug in. So in the derivative given, we have this 2x minus y. Well, what is y equal to? Y is equal to that whole expression. So we can just substitute it in. When two things are equal in math, we know that we can just do substitution. So I have 2x minus 3e to the negative x plus 2x minus 2. And then we can just simplify it. Let's distribute that negative across. 2x minus 3e to the negative x minus 2x plus 2. What do we notice now? The 2x's cancel. And what we are left with, negative 3e to the negative x plus 2. Have I shown that those two things are technically the same? Yes, what's on the left-hand side is the same as the right. Don't need to explain it, don't need to like draw arrows, you could if you wanted to. But just showing those steps is going to be enough. Questions there? All right, let's do one more slide. I am going to kind of go out of order in the notes. And I'm going to jump over to the tab that says increasing, if you are following along in OneNote. I also realized I didn't erase this when I shared it from my BC class, so I'm going to pretend that all that's not there. And so I try to find like the last thing we'll do in notes, and we'll finish these on Wednesday. I definitely don't want to rush it and try to cram too much in one day. These differential equations, they are first derivatives. So anything we have ever done with a first derivative, we can do with a differential equation. Like I could find a tangent line. Kind of easier, so you don't have to worry about finding y prime, because it will be given to you. You know what the derivative is. I could talk about intervals of increasing and decreasing. I could talk about relative extrema. I could talk about a whole lot of things relating to that first derivative. Try to pull out one that I think is a pretty common one. So it says to consider the differential equation, dy dx is equal to x minus y. I did generate the slope field on this page. Normally that wouldn't be provided to you, but I do think it's nice to see a computer generated slope field. So that's what the slope field of that differential equation looks like. What's important though is we're able to pull from our knowledge the calculus fact this is asking us to find. So we want to describe all the points at which the solution curves would be increasing. When you see that phrase solution curve, you're just talking about the original function. So basically we're trying to find when is the original function increasing. What calculus fact do you know about increasing functions? What's positive? The derivative. So what should jump out in your head? You see this, and you should automatically know, hey, this means the derivative is positive or the derivative is greater than 0. Well, look at this problem. What is the derivative? That, what's given to us, dy dx is the derivative. So if I want to talk about when this curve is greater than 0, basically what needs to be greater than 0? X minus y. I could change that up a little bit, like I might say, hey, find where the curves are decreasing. That would be when the derivative is less than 0. Or maybe I could say like, hey, where are there horizontal tangents? That would be when just the derivative is equal to 0. And then we want to somehow make this usable. To me, the most usable form is when y is by itself. So like adding both sides with the y, I get when x is greater than y. Me, I like flipping it around, and I see when y is less than x. It does tell me to describe. We're not going to be fancy with it. Basically, whenever that inequality is true, this original function, which we don't know what it is, would be increasing. So basically, whenever the y-coordinate is less than the x-coordinate, this graph would be decreasing. So how am I going to describe it? Here's my fancy way of describing it. All points where, and then that statement is true. There's other ways you could describe it as well. I'm going to go to the graph to kind of show you a way that we can think about it. Let's stretch our minds back to Algebra 1, actually. Y is less than x is an inequality. You learned how to graph inequalities back in Algebra 1. When I'm graphing y is less than x, that's the same thing as graphing y is equal to x and then trying to figure out which side to shade on. Well, y is equal to x is going to be this diagonal that I didn't erase before I distributed it. Why would I use the dotted line? This is less than, not less than or equal to. Which side should I shade? Which side is going to be when y is less than the x? below the curve. And I have the slope field here, so normally a question like this, you wouldn't have the slope field. But I think it's nice when you're looking at this slope field, I guess my highlighter is just not gonna work. So let's just pretend I shade the whole part. What do you notice about every slope field underneath that dotted line? They're all increasing. So like our algebra does check out. Like, yes, that is when the derivative is equal to 0, or excuse me, is less than 0. Some other neat things you see, like what do you notice about all the slopes on that diagonal line? They're all horizontal. They're parallel to each other, they're horizontal. Why would that make sense? Well, if the derivative is horizontal, that's dy dx is equal to 0. If dy dx is equal to 0, you just get x is equal to y. So basically, whenever the x and y are the same coordinates, it's going to be a horizontal line. That is where I'm going to stop at today. I will say this unit is going to require like a lot more just like thinking of you necessarily than like what the previous unit did. What we're going to pick up on tomorrow is we are going to look at one that deals with concavity. I realized after first period today that people in GAFs did not learn implicit differentiation, so I will have to do like a quick mini lesson on that. It's probably good to review for those who have any first semester anyways. So we'll do a quick review of implicit. We'll do the concavity example, and then we'll go back and do tangent line approximations. But that is where I'm going to go ahead and stop today's notes at. You can start homework 1. You can do all of the front page and most of the back page, except what is referring to a second derivative. Other reminders, you can do unit 7 or 8 recovery this Wednesday during office hours. Infinite campus grades should be fully updated. If your briefcase binder grade is not 100, see what you're missing, redo it, let me know, and I'll kind of give you your points back. Again, some people have gotten a little bit lazy with the briefcase binder, but that's a really good way to get your grade up if it's not a 100, since it is counting in that summative section. And I am supposed to give an asynchronous assignment if you're not taking the ACT. I'm not going to be checking it, but my unofficial asynchronous assignment for those not taking the ACT is to go to that AP exam review tab in OneNote and find 15 multiple choice questions to do. But I don't have time to check it, so if you do it or not, I won't know. But that's going to be my unofficial assignment for those of you not taking the ACT. Might be a good idea for some of you to pick some of the derivative ones to review anyways with the unit that we're on. But we'll finish these notes on Wednesday. Nothing really that we're going to be doing tomorrow, of course. I'll be proctoring the ACT. But we'll finish these notes up on